What I want to do now is I want to insert my perturbation, the expression for the perturbation. So if I now just look at this alone for a moment and insert the perturbation, then I get a dipole moment operator, scalar product with the field, and actually I get this integral over frequencies, and I get a minus sign and a half. So let's put that all in. Now I want to write, instead of writing with the scalar product, I want to write the scalar product out as a sum over the three components, x, y, z. So this is going to be a sum over components beta, which are x, y, and z. Then I have minus 1/2, comes from minus 1/2. The scalar product I write as a sum. Then I get my response function. Oh, let's have some space a bit around it. I have my response function with the alpha component of the dipole moment operator. And I have to put that in. Now that integral over the frequencies I can take out. I mean, this is an integration over space. So I can, and I have some time operators in here, or time-dependent operators, but there's nothing with frequencies in here, so I can take that integral over the frequencies out. Minus infinity plus infinity, and get some d omega somewhere at the end. Then I also can take this one out, e to the minus I omega t. The f, that's just a component of the field. That's not acting on any electronic wave function. So I also take this out, omega, but I mean that was part of a scalar product, which I write as a sum. So that's going to be the beta component. And now I finally should be able to, and what is left now from my perturbation up there is the beta component of mu. That's the only thing which is I haven't considered yet of this perturbation. So I get E h0 t minus t prime divided by I h bar mu beta and e to the minus h0 t minus t prime divided by I h bar. Right. So now I have only things inside of this response function which actually are acting on the electronic wave functions. Here. And here I have this Fourier components of my field, which we had. I mean, basically this thing is just Fourier components of the time-dependent field. And you can see, in order, the definition of the induced dipole moment is one which has an integration over frequencies and not an integration over time. So what I finally then do is I also use a Fourier transformation on my response function. So the second thing I want to do is the Fourier transformation of the response function from the time to the frequency domain. So I can have Fourier components, a response function in the frequency domain, omega, which is then the same as having the response function in the time domain, which is this thing, or this one here. G prime, IH bar, mu beta operator, e to the minus h bar t minus t prime divided by IH beta. And then whenever you have a Fourier transformation, I mean, you have this exponential, omega t prime minus t prime. So this is the Fourier transformation going from the time domain to the frequency domain. And if I insert that also, if I use that here, then my time integration disappears because I went over to the frequency domain, and I finally end up something which I have to write here now. I end up that my alpha component of a time-dependent dipole moment is the permanent contribution plus 1/2 sum over beta, and now that integral over frequencies from minus infinity to plus infinity. Now the response function in the frequency domain, mu alpha, and I take the minus sign which I had here, this minus sign, which is the minus sign from up there. I take that in my response function, beta, and then I have the field components, beta, omega, and I have e to the minus I omega t d omega plus higher order terms. And I want to do two things more. I can go back to, the difference between this expression, which is the one I want to compare it with, and that expression is now again that here I have from minus infinity to plus infinity, and up there I have from 0 to plus infinity. And I needed to extend that integration up there for the field in order to really have it as a Fourier transformation. But now we can go back to the original cosine expression. And then I get 0 mu alpha 0 plus sum over beta from 0 to infinity, my response function in the frequency domain with two dipole moment operators, the beta component of the field, cosinus of omega t d omega plus higher order terms. And if I compare that with the expression, the classical expression for the dipole moment, then I can see that this this response function is actually the alpha beta component of the frequency dependent polarizability tensor. So what do you do in order to derive expressions like this, or similar for other properties? Essentially what you do is you have a definition of the property, which is this one here, which is the classical definition. And then you try to recreate that by doing time-dependent perturbation theory until you end up with an expression which looks very much the same and allows you to identify how this alpha, how the polarizability looks like. And here the permanent dipole moment. I mean, the permanent dipole moment we knew already for a long time. That is just the expectation value of the dipole moment operator. And then the polarizability is a linear response function.